This is week 4, screencast 2, 571. I was working on the formula to estimate when the process shifted on an X bar chart. And I've got this formula down here that has some funny symbols in it. So what's the deal? Well, mu hat equals stage 1 X bar bar. So the average of the stage 1 subgroup means is mu hat. That plays the role of the best guess of the true mean, because we were in control in stage 1, and that's the average that we computed once we'd eliminated out of control points and recomputed everything. So what's this animal X bar bar T to T? Well, it is the average of all stage 2 X bar I values from I equaling T through I equaling uppercase T, which is T sub n naught. So this is the latter average of the observations on X bar from the point T up through the point at which you got signal, i.e. T sub I T sub I between and including T and uppercase T. See, so this T is not indexed because it depends on which one you're talking about. Note from raw observations, you'll have a question of, well, how do I compute T for a subgroup when in fact the observations inside the subgroup were taken at their own particular time points. So in general, what people do is they let T for a subgroup be the average of all time points within that subgroup. So if you have a subgroup size of 4 and you take observations at 1 o'clock, 1:15, 1:30, and 1:45, you'd average those 4 time values to get the time for that subgroup. So let's look at just half an example. I'll call it start of an example. Time points. They are 1.2, 2.5, 4.8, 6.7, and 8.3. size 3 subgroups. With associated means of 4, 2, 3, 9, 12. First 2 subgroups are in stage 1. Hence, K equals 2. Remember K? K is the number of observations, number of subgroups in, stage 1. Say T naught, T sub n naught equals T equals 8.3. So you got signal on this last time point, last subgroup. What's this n naught business? Well, n naught equals the number of stage 2 subgroups up to and including the subgroup that gave signal. Use T equaling 4.8, 6.8, 6.7 rather, in the test function. So a lecture question is, what is the value of the test function in at the time point 4.8 and at the time point 6.7? And then what do you conclude as your estimate of T shift for this example? Okay, so cleaning up a few things here. The next thing that needs to be mentioned is the all-important average run length, ARL. So anybody who knows anything about control charts is going to toss around the acronym ARL and assume that you know what they're talking about. So it is the expected number of subgroups before signal, before you get a subgroup that gives you a signal. So who cares about that? Well, you want to know on average how long will a control chart run before it squeals on you. Well, maybe it should squeal. That's fine, but that's called an out-of-control ARL. But what if it is, and why should that happen? Well, if the mean shifts. So if the mean shifts, you're out of control, and you'd want the chart to give signal. But let's say you're cruising along with some mu, and down here is your mu hat, because you blew it and got a bad data set on stage 1, and so you estimated mu to be some value other than what it really is. You're just thinking, well, that'll never happen. That happens all the time because you're estimating mu. There's no guarantee that you're going to get a value right on mu. And so you're cruising along, and somebody says, you know, running this control chart is a big waste of time because it never gives signal. Why are we doing this? Your answer is, well, so this is X bar, you know, your standard X bar chart. The in control ARL of an X bar chart running plus minus 3 sigma X bar limits. Okay, so notice that I say running excuse, a particular false positive rate based set of control limits is 1 over the false positive rate, which in this case is 1 over 0.0027, which if you crank that out on your calculator, you'll get 370. So 370 what? 370 subgroups on average will be plotted before the chart does what? Gives a false positive. Because you're in control. That's what that means. So 370 subgroups will plot before one gives signal on average. On average. In this case, the signal will denote a false positive. False positive, you know, what's false positive rate? Well, it's the rate at which, or the probability that you get a false positive. So you can turn that around and say, well, I don't know what I don't want to know what the probability is getting a false positive on any one subgroup. I want to know how long this chart's going to run before it trips falsely. Excuse. So the answer is just do 1 over the false positive rate, and you'll get a number, which is how many subgroups will plot before you get one that erroneously tells you that you've gotten a mean shift. In fact, you have not. The process has not shifted its mean. The chart has just told you a lie. It's cried wolf. So you would want the chart to never give you a false positive. But that's not going to happen, because in order for that to happen, you'd have to have control limits that were set at infinity and negative infinity, making sure that points never plotted above the line, well, out of the control limit band due to just noise. But then the chart would be useless, because it would also never give a signal when in fact the mean did shift. So what you want is you want the in control, so I'll say you want the in control ARL to be real big, because you don't want this chart giving you a signal and having you chase around after problems that don't exist. But you want the out of control ARL to be very small. Now, if you're thinking about what I've been doing in this screencast and the last one, you're going to say, well, hold it now. We just talked about that. If you, what we've already talked about is this, that we were going along just fine in stage 2. Here's stage 1, and here's stage 2. We got a shift in the mean, and this point is the true value of t shift, and we got our signal, you know, maybe here. And didn't we just talk about how long it took the chart to notice that the mean had shifted? Yes. Well, isn't that what the out of control ARL is? Okay, you do a shift, and now you want to know how long the chart will run before you get what is called in the stochastic processes world. You want to know what's the time point of what's called the first crossing, and that's when the process strays outside of a particular band of values. In this case, the control limits. True, but the difference is this A. This is standing for the word average. And you've got to be careful to not use average values in management when you're trying to come up with a specific estimator, an estimator for a specific event, which in a case of the actual use of a control chart will be a particular pattern of values. So you could be going along here, and you could have points that drift up. That will be a different occurrence than if you have points that do this and then suddenly shift, because there was a time delay to the consequences on the rest of the process due to that mean shift. So the pluses is a different run of reality from the dots. These two sets of values will produce different values of the estimate. But the out of control ARL is an overall consistent or general property of the control chart. And the absolute value of mu hat minus mu, which is a mean shift, is expressed in terms of multiples of sigma x bar in order to make it dimensionless. Specifically, k sigma x bar. And in this case, k does not stand for the number of stage 1 observations. We talk about a 1 sigma x bar mean shift. That means mu has changed its value to the tune of 1 times whatever we estimated the standard deviation of x bar to be. Now remember, we know the standard deviation of x bar because we had to compute it to get the control limits. So if we're measuring in voltage, millivolts, or we're working on high voltage transmission equipment, we're working in terms of kilovolts. The use of a multiple of the standard deviation will remove the dimensions from the discussion, and we're just going to talk about this K. So you're talking about a 2 sigma mean shift, as it's said in the vernacular, or a 3 sigma, or a 1 sigma. You got to tell me, because I can't compute the out of control ARL unless you tell me how big the shift is. Well, why do you need to know that? Well, look, it's kind of common sense that if you have a big giant shift in the mean, that the time from the signal to the point at which you shifted, on average, this is going to be small if this is big, because the chart is going to quickly respond to a giant shift in the mean. For a big enough shift, you won't even need the chart, because you'll be making scrap and you'll have to shut the line down as fast as you can. But if you've got a teeny tiny shift, it might take the chart a long time to notice that. So in this case, you get your signal out here. It might take a long time. So I'll say T shift big, T shift so this is the T shift, and you have signal big shift, and here you have a small shift. In other words, the chart is going to take a lot longer to respond to a small shift than to a big shift. Kind of begs the question, is there some way to compute this the amount of number of subgroups that will go by on average after a shift, whether small, which is this interval here, or from a big shift, or from a small shift, which is going to be this interval right here. And yes, there is. I generalized a formula in Ryan, and I'll give it to you right now, that gives you the out of control ARL for after a K sigma X bar mean shift. And that formula is, so this out of control ARL is 1 over P probability that Z is less than Z lower plus I blew it. It's 1 over, big giant 1 over, probability Z less than Z lower, plus probability that Z is bigger than Z upper. Where Z lower equals mu plus 3 sigma X bar minus quantity mu plus K sigma X bar the whole thing divided by sigma x bar, and z upper equals the fraction mu minus 3 sigma x bar minus quantity mu plus k sigma x bar, whole thing over sigma x bar. Notice that these two formulas are the same except for in the first formula for z lower it's mu plus 3 sigma x bar, and in z upper it's mu minus 3 sigma x bar. And I've got these, I knew there was something wrong. I've got these backwards. This is z upper, and this is z lower. So even with all my messing around, I think I've got the thing correct now. And notice that the k up here is right here and here. Don't forget the k in the screencast.